Hello everybody and welcome to section 12.2, which is all about the conic, specifically the ellipse this time. And again, I want to point out to you that the circle, ellipse, parabola, and hyperbola, focusing today on the ellipse, is formed when a plane intersects a cone. And last video we talked about when a plane was perfectly perpendicular, we created a circle. When a plane is at an angle less than 90 degrees and it intersects a cone, it creates more of an oval shape or an ellipse. And to see how this is created, let me click on that same link that I had in the last video, which is also on Schoology. So if I click on this, see if I can find where the ellipse is started. Okay, so if we take a look, the plane is intersecting the cone, and as it goes up and down, notice that the ellipse gets smaller the closer it gets to the center here, but it does create an oval shape. So if I pause this and go back to our notes here, that is really how an ellipse is formed, so this link is here if you need it. But also that, what we would like to do with the ellipse today is talk about how we can graph it if it's in standard form, like the circle. We also want to talk about and identify an ellipse when it's not necessarily in standard form, so we may need to complete the square again today. If it's a general second degree, when to recognize it, and how to convert it to standard form. So at this point, I'd like to focus on the analytic geometry definition of an ellipse. Given two fixed points called foci, so I'll call this F1 and F2, an ellipse is a set of all points in a plane such that the sum of the distances to each fixed point is constant. And I'm going to show you a video in just a minute. But what that means is if I have a point, the distance from this point to focus 1 and this point to focus 2 would be, the sum would be the same as if I had another point over here. If I drew from this point to this focus and this point to this focus, these two distances together would be the same as the two blue distances together. If I continued that and drew a distance from here and then to this focus, these two lines would be, the sum of them would be the same as the red and the blue. And so eventually you would create a shape that looks like an ellipse or an oval. But to show you this in a different way, let me click again on this link that I found that might be helpful. So if you take a look at what this lovely mathematician did, here's focus 1 and here's focus 2. And this point is constantly moving, and the green and the red distances are different, but notice down here that the sum of the green and the red distance is always the same. That is how an ellipse is formed, when the distances are the same. However, so when the sum of the blue is the same as the sum of the red, which is the same as the sum of the green, that creates points all along here that are all same distances, which creates an ellipse. So that is really how it's formed. And the reason I mention this to you is for those that have studied ellipses before, you might always be wondering, why do the focal points or why do the foci matter? These are the reasons why the ellipse can be drawn in the first place. So to transition here to the first example and some vocabulary, what I'd like you to do is star A. A is the distance from the center to the major vertices, and this is very important information. B is the distance from the center to the minor vertices, or the smaller vertices, versus A is the larger vertices. Plus or minus C, so distances in both directions, is the distance from the center to the foci, and again the foci matter because that's how you form an ellipse. The Pythagorean Theorem is learned or used to find the relationship between A, B, and C. And remember, whichever denominator is larger determines the major axis. And so if I had a general form here for a horizontal major axis, that means that this has to be the A term. So if it's horizontal or x-based, the A must be underneath the x, versus if it's vertical or y-based, the A term has to be underneath the y. So if I looked at this first example, I notice that the larger of the two values is underneath the x. So that means that I know that this ellipse will be horizontal. So what I'm going to do is star A, because A is always the distance from the center to the major vertices, and A in this case is my larger number, and because 64 is really A squared, the A value must be 8. Which means that my B value is my minor or smaller vertices or smaller axis, and that comes from the second number here, and the square root of 9 is 3, so my B value would be 3. The center works just like a circle. It's the opposite signs. So the center here would be 2, comma. Well, there's no parentheses, which means there's no movement. So my center is 2, 0. So if I come over here to graph 2, 0, that would be my center. And then the A and the B do help graph, or at least start to graph my ellipse here, even without the foci. A, again, is the distance from the center to the major vertices, and they're on the major axis. So from my center, I would go 1, 2, 3, 4, 5, 6, 7, 8 in each direction, because the x-axis has to be the major one, because this is a horizontal ellipse. 1, 2, 3, 4, 5, 6, 7, 8. Now from the center, the minor axes, I would go the other way. Because the y is not the main axis, it's going to be shorter. And I'm going to go up 1, 2, 3. I'm going to go down 1, 2, 3. And then I'm going to connect all of these dots here, and this is going to form my ellipse. Not the best drawn, but again, it'll do. So these green dots here represent your major vertices, and those 2 points are at -6, 0 and at 10, 0, because they're 8 units away from the center. And my 2 red dots here are my minor vertices, because it's on the shorter axis here. And those points are going to be at 2, 3 and 2, -3. In order to find my C, or my foci, we're going to use this Pythagorean theorem identity. C squared is equal to A squared minus B squared. Well, I know that A is 8. So C squared would have to be 64 minus B squared, which would be 9. And yes, those did come from the equation. So my C would really equal, C squared would equal 55, which means that my C is the square root of 55. Now, something you need to know about the foci is that the foci, in order for this to be formed, have to be on your major axis. So because my major axis is x, I'm going to do this in yellow, or at least to start in purple, I guess. My foci are going to be somewhere on this major axis here. And so if I would like to find the coordinates of the foci, I have to go root 55 in each direction. So how we could write our points is we start at 2, so it would be 2 plus the square root of 55, but the y doesn't change to stay on this axis. So it'd still be 0, and then 2 minus square root of 55, 0 would be the other coordinate of your foci, because it has to again be on your x-axis. If you would like to see what these are in terms of decimals, this first one I've already calculated. That would be 9.42, 0, and 2 minus root 55 is -5.42, 0. And so if I graphed those to the best of my ability, this first focus would be 9.72, like really close to that green dot there, and this focus here, -5.42, would be really close to that major vertice there. And so that's our first picture of an ellipse. On to our second example. I want you to notice that this is not in standard form. So I'd like to write up here really quickly before we get to this, what makes an equation an ellipse? Well, a circle was if A equals B. So everything depends on these square terms. In order to recognize an ellipse in not standard form, it's if A does not equal B this time. And so there is a different lead coefficient, but the same sign. So to show you what I mean, on this next example, if you look at the two squared terms, we have two different lead coefficients, 9 and 4. However, both terms are positive, so I can identify this as an ellipse before I begin. Speaking of identify, what I'd like you to do is pause your video, and I would like you to complete the square just like we did for circles, and get at least as far as you can. Move the 36 over, take out the greatest common factors, and I'm going to come back with you and show you how this differs a little bit from a circle. So please pause now. All right, guys, so first I subtracted the 36. I got my x's together, got my y's together, took out a GCF of 9, completed the square, and got 9 times x plus 2 squared, took out a 4, completed the square, 4 times y minus 3 squared, added these terms on this side by distributive here, and I ended up with 36 on the right side. So this is the point I would like you to notice that we have some coefficients in front of my parentheses, which I don't want there. And if I go back to the previous example, I would also like you to notice that this example in standard form was equal to 1, and these two examples are also equal to 1. So in order to have an ellipse in standard form, we need it to be equal to 1. So what I'm going to do is divide everything by 36, and I would reduce. So I would get x plus 2 squared over 4 plus y minus 3 squared over 9, because it's 4/36, equals 1. And so this is my ellipse in standard form. And now that it's in this form, now I can determine what kind of an ellipse it is. And what I notice is that this is the larger number underneath my x and y terms. So because the 9 is underneath the y's, this ellipse will be vertically based. And so that means that the 9 must be my a term and the b must be my 4 here. So my a, number 9 is really a squared, so my a term is 3 and my b term would be 2. My center would be at -2, 3. And so what I can do is graph that point first. So I'm going to graph -2 up 3. And then I'm going to star A, because remember that is the major axis, because it's the larger one. And because this time it is a vertically based, I'm going to go up and down 3, because that is the larger axis. If I switch colors, the B or the minor axis, I would go 2 in each direction. So this one looks a little bit more circle-like, but not quite. And so I would connect all of my dots. Easier said than done than on this computer. I'm going to make these dots a little bit bigger. And I'm sure your picture might be a little bit neater than mine. So now if I look at my picture, my major vertices on the major axis, which I will highlight here in blue, would be the point -2, 0, and the point -2, 6. My minor vertices are on my non-major axis, would be the point here in blue, which is 0, 3, and this point in blue, -4, 3. My C, or my foci position, or the distance from the center to the foci, is determined by using the Pythagorean Theorem in a way. C squared is equal to A squared minus B squared. So C squared would equal, A squared is 9, B squared is 4. So C squared would equal 5. So that means that C equals the square root of 5. And here we just need to be careful about our foci, that the foci always start is the distance from the center on the major axis. So we're going to be going up and down this time, root 5. So that means that my x in both of these foci is going to stay at -2, but my y's are going to change, and they both start at 3. So it would be 3 plus root 5 and 3 minus root 5. And as decimals, because I did this as well, it would really be the points. The first one would really be -2, 5.24, and the other one would be -2, 0.76. And so just to see if those fit in, -2, 5.24 would be a little bit again before that red dot on the major axis, and -2, 0.76 would be right about there. So there's a picture of a vertical ellipse. The last example I'm going to have to do on another video. However, I'd like to point out before this video ends that all equations of an ellipse always has a plus in the middle. And I've noticed over the years that the Pythagorean Theorem relationship is the opposite sign. So that's good for a memory trick. If an ellipse is always a plus, that means the Pythagorean Theorem relationship has to have a minus in it. Please just keep that in mind as we keep going. But there's going to be another short video just finishing the last example. Thanks for sticking with me.